Hey everyone, in this video we are going to talk about various pipeline hazards and the methods of their resolution. So continuing our discussion of pipelining, there are three main kinds of hazards that can occur in a pipeline. Resource conflicts, also known as structural hazards, data dependency conflicts, also known as data hazards, and branch difficulties, also known as control hazards. Then we'll take a look at some methods that have been designed to overcome or resolve these issues, these hazards, and then we'll take a look at some problems. All right, let's begin with pipeline hazards first. Now, difficulties that can cause the instruction pipeline to deviate from its normal operation are of three main kinds. The first one is resource conflicts. This happens when access to memory is done by two segments at the same time, right? So when two or more segments of the pipeline are trying to access memory at the same time, resource conflicts occurs. These conflicts are also known as structural hazards. Then there are data dependency conflicts. These arise when an instruction depends on the result of previous instructions. Now, as you know, instructions use the results of previous instructions, and then results of their operations are used by further instructions. There's a chain of sequence involved, and when a specific instruction cannot execute as long as it receives suitable input from the results of the previous instruction, data dependency conflicts occur. They're also known as data hazards. Then there are branch difficulties. They arise when branch and other instructions change the value of program counter. So as long as PC is incremented by 1, everything goes normally. But when a branch is encountered, an instruction that suddenly changes the value of PC from PC plus 1 to something else, then branch difficulties occur. They're also known as control hazards. Now we're going to talk about each of them one by one. Let's first start with structural hazards. Structural hazards. Now here's an illustration of what that looks like. Suppose we have 4 instructions and each instruction occurs in 4 stages, right? So instruction fetch, instruction decode, instruction execute, and some memory operation. Now you see, in both instruction fetch and memory operation, memory is used in all of the 4 instructions. Now this is a typical cycle. With cycle 1, instruction 1 is fetched. With cycle 2, instruction 1 is decoded while instruction 2 is fetched. With cycle 3, instruction 1 starts executing while instruction 2 moves on to the next phase, which is decoding, and so on and so forth. Now if you look at this scenario, in cycle 4, this one, first instruction is trying to write its result. This is the final stage of this instruction. So basically, after execution, it might be trying to write the results of its operation into memory. The idea is memory is being accessed. And then during the same cycle, instruction 4, it's being fetched from the memory. Now you see, both of these operations are on the memory. They are trying to access the same resource. The resource in this case is memory. So there is a resource conflict. So until instruction 1 stops using memory, instruction 4 cannot be fetched from memory. This is caused by structural hazards. This is a resource conflict. Now to avoid this problem, I4 must be kept waiting until memory becomes available. So I4, because I1 entered the system first, entered the pipeline first, and I4 came later, so I4 will have to wait until I1 is all done and finished with memory, right? So I4 must be kept waiting until memory becomes available. This wait introduces stalls in the pipeline. So like this, right? So it should have been like this. With cycle 4, instruction 4 should have been fetched, but it can't. So it waits all of these stalls. So 3 stages are wasted, 3 cycles are wasted. I4 could have started earlier. If it had started earlier, it would have finished earlier, but now there are stalls. So this is the biggest problem caused by structural hazards. Now to minimize structural dependency stalls in a pipeline, a hardware mechanism called renaming is used. Now what happens in a renaming? See, renaming is a very simple process whereby memory is divided into 2 independent modules, code memory and data memory. So what you do is, we have the same physical memory, it's divided into 2 parts. In one part, only instructions are kept, it's called code memory, and in the other part of the same memory, data is kept, only operands are kept, it's called data memory. Now what happens is instructions will be accessed from this part of the memory, whereas all other data will be accessed from this part of the memory. Now, albeit they are same physical memory, but since we have divided them into two different modules, they can be accessed simultaneously. So that means that if one instruction is being fetched from the memory, the other one can be performing its data writing part at the same time during the same cycle. The next kind of pipeline hazard is data dependency. Data dependency occurs when an instruction needs data, including addresses, that are not yet available. So instructions, what they use normally is either data, operands, or addresses. Now, if an instruction requires some data immediately, without which it cannot proceed, and if that specific data is not available at that time, this means there's a conflict, there is a hazard. This is called data dependency. For instance, consider an instruction, it is currently operating it in its FO segment, fetch operand segment, right? So this instruction may need to fetch an operand that is being generated at the same time by a previous instruction which is currently executing in its execute instruction, right? So instruction 2 requires some operands, but those operands haven't yet been generated by instruction 1. So instruction 1 is in execution state, whereas instruction 2 is in fetch operand state. Naturally, the second instruction will have to wait until the operands become available. Another way this kind of dependency occurs is if an instruction with register indirect mode cannot fetch an operand if the previous instruction is loading the address into register. Now you have register indirect instruction modes, right? So such an instruction cannot fetch an operand if the previous instruction is loading the address into register. Again, it will have to wait. So this happens, this results in data dependency. Now, there is an example of such a condition of data dependency. Consider we have two instructions. One is add, one is subtract. So what's happening here is the contents of R2 and R3 are added and moved to R1. And in instruction 2, the contents of R1 and R2, again, this is the same R1, right? So first something is added to R1 and then that content is taken, something is removed from that, and the results are stored into R4. Now, when these instructions are executed in a pipelined processor, data dependency condition occurs. Because I2 tries to read the data before I1 writes it. I2 needs one of the operands is R1. This operand is actually created when add instruction is executed, right? So if this is, say this is the pipeline. So instruction 1 is fetched, it is decoded. While instruction 1 is being decoded, instruction 2 will be fetched, right? Then third clock pulse occurs and instruction 1 is executed. Instruction 1 is the add instruction. This is where add instruction is executed. So it is being executed at the moment. That is, R2 and R3 are being added, but they haven't been written into R1 yet. That means R1 is not available. But at the third clock pulse, I2 has already moved to its second phase, which is instruction decode. It needs R1, but R1 is not yet written, and since they are registers, there will be some kind of garbage value available in the register. So what instruction 2 does is it simply takes whatever value it finds in R1, because it has to execute, right? So it takes whatever value it finds in R1, it keeps it with it, and then it starts executing. So it executes this operation with whatever old value of R1 it could find, whatever value of R1 was present from some previous time, any garbage value. It just takes it up and starts the subtraction process, because the actual R1 will be available after cycle 4. But during cycle 4, I2 is already executing, right? So this is the problem caused by data dependency, and this is a major problem. If we are performing arithmetic operations like these, where the following instructions need to use data generated by previous instructions, and if those data values are not yet available, then all the calculation can become completely wrong. All right. Now, data hazards. There are three main kinds of data hazards, and these are RAW, read after write, WAR, write after read, and WAW, write after write. Now see, Data hazards occur when instructions that exhibit data dependency modify data in different stages of the pipeline. So depending on which instruction is trying to modify the data in which way, because you can either read the data or you can write it, right? So depending on which instruction is reading it and which instruction is writing it, we can have these three kinds of dependencies. Let's take a look at each of them individually. Let's start with RAW. RAW is read after write. Now if we have two instructions I and J, I comes first, J comes second. RAW hazard occurs when instruction J tries to read data before instruction I writes it. So it's clear from the name itself, read after write. When J tries to read data before I has written it. For instance, if we have instructions like these, first I occurs, then J occurs. Now what's happening in I? R1 plus R3 moves to R2, and in J, R2 plus R3 moves to R4, right? So this register is going to be used here. But what happens if I hasn't finished writing its data and J tries to read it? Then RAW hazard occurs. Then the second type of data hazard is WAR, write after read. Now again, we have two instructions, I and J. I comes first, J comes second. WAR hazard occurs when instruction J tries to write the data before I reads it. Again, consider an example. Suppose this is instruction I. R1 plus R3 should be moved to R2, and J says R4 plus R5 should be moved to R3. Now you can see what's happening here, right? WAR hazard occurs when instruction J tries to write the data before instruction I reads it. This is supposed to go first. That means whatever value was in R3, maybe from some previous computation, is what's supposed to be added to R1, and that's what's supposed to move to R2. This writing of R3 is supposed to take place later, right? So maybe there was a previous value of R3 and that is the one we were supposed to add. But if J tries to perform its operation before I can complete it, then that means R3 will have a wrong value. It will have a value that we do not want. Right? We don't want this value of R3. We wanted some other value from some previous computation. So this is where WAR hazard occurs. The third kind of data hazard is WAW, write after write. Right? So both are trying to write. Again, we have two instructions, I and J. I comes first, J comes later. WAW hazard occurs when instruction J tries to write the output before I writes it. Now both of them are writing. In the previous two cases, one was reading, other was writing. Now both are writing. Again, consider an example. I instruction requires us to add R1 and R3 and write the result to R3. And then J instruction is supposed to add R4 and R5 and write it to R2. Now you can see that both of the writing is being done to the same register. So the final state of the register will depend on which instruction is allowed to write into it first, right? So sequentially, I is supposed to go before J. That is the correct sequence of operations. But if it doesn't happen that way, then a WAW hazard occurs. There are several different methods by which we can deal with such data dependency conflicts, and these are the ones we're going to be talking about: hardware interlocks, operand forwarding, and delayed load. Now let's first see what hardware interlocks are. So this is the most straightforward method of dealing with data dependency conflicts. What it does is it entails insertion of hardware interlocks. Hardware interlocks are circuits that detect instructions whose source operands are destinations of instructions farther up in the pipeline. Simply stated, what this means is this is a special circuit which is introduced into the pipeline, and the main task of this circuit is to check all of the instructions and make a proper analysis of which instruction requires operands from which other instructions, right? So whenever there are any instructions whose operation depends on attainment of operands from a previous instruction, that is what a hardware interlock detects. Now when it detects such situations, instructions whose source is not yet available is delayed by enough clock cycles to resolve the conflict. Now it's very simple to understand. Consider this sequence of instructions. This is a hypothetical sequence of instructions. We have instruction 1, addition. then there is another instruction in between, then there is instruction 3 which is a subtraction operation, and then there is instruction 4 which is a multiplication operation. Alright, now you can see that in addition R2 and R3 are used, the result is stored in R1. Then the subtraction operation is fine because it uses R4 and R5 which have nothing to do with addition instruction. The results are stored in R6, and then in case of multiplication what happens, there is another register R8, and this register R1 which is written after the execution of the first instruction is used. So this R1 is going to be used, the contents will be multiplied with R8 and the result will be stored in R7, right? In this case what happens is R1 is a source operand for I4, R1 is a source operand for I4 which is also the destination operand for I1. So there could be a possible conflict depending on whether I4 will start before I1 finishes. Alright, the hardware interlock will detect it, and then it will try to delay I4 by enough clock cycles just to make sure that by the time this starts, R1 has been successfully written by I1. Another way of dealing with data dependency conflicts is operand forwarding. Alright, this is very useful and also very interesting. So what happens in operand forwarding? It entails the use of special hardware to detect a conflict, data dependency conflict, and then avoid it by routing the data through special paths between pipeline segments. Alright, interface registers are placed between segments to hold intermediate outputs. Dependent instruction can access new value from the interface register directly. So a very simple way to understand this is with the help of an example. Alright, suppose we have two instructions, add and subtract. What's happening in the add instruction is R2 and R0 are added, the contents of these two registers are added, the result is stored in R3. And then there's a subtract instruction in which 8 is subtracted from R3 and whatever result is, it's stored in R4. Now let's try to understand how these two instructions will be executed in a pipeline normally and with operand forwarding. So I say it normally because so far we have not even talked about the concept of operand forwarding. So this is like regular before the introduction of the concept of operand forwarding, and this is with operand forwarding. So normally if it would have happened, what would we see in this pipeline? The first clock cycle occurs and the first instruction is fetched. So add is fetched. When the second clock cycle occurs, add will move on to the next phase, which is decoding, and also the new instruction will be fetched, right? So in clock cycle 2, add instruction is decoded and subtract instruction is fetched. Then clock pulse 3 occurs. So the add instruction will then move on to the next phase where the operands will be read, right? Operands will be fetched from memory. At the same time, during clock pulse 3, instruction 2 will be decoding. So the decoding process will begin for instruction 2. Now, when clock pulse 4 occurs, instruction 4 will start instruction 1 will start executing, right? The add instruction will start executing normally, and during clock pulse 4, subtract instruction should have started fetching its operands. It should have started fetching its operands, but the operand, one of the operands, is not ready yet. It won't be ready until this instruction is fully executed and it writes its results into memory, right? Only then the second instruction can fetch it and start its operation. So while this happens, the subtract instruction cannot proceed because it does not have the necessary operands, so it waits. And then fifth clock cycle occurs and instruction add is now, it has finished execution, it is now writing its results, right? At the same time, instruction 2 is still waiting, because until this point, until the sixth clock cycle starts, these results, whatever add is writing, will not be available to anyone, right? So again, during the fifth clock cycle also, subtract instruction is waiting, so we have 2 stalls. And then the sixth clock cycle occurs, and then the subtract instruction is able to read the operand, and then the next clock cycle occurs and the subtract instruction is able to execute, and then it is writing its results. So this is how it would have been normally, right? We have 2 stalls and it's taking 1 2 3 4 5 6 7 8 clock cycles to execute these 2 instructions, and that is only because they have an operand in common, right? Add needs to write this so that subtract can read it. Now let's see what happens in the same situation if we had used operand forwarding. Operand forwarding, the hint is in the name itself. The operand is forwarded to whatever instruction needs it before that operand is written into memory. Let's see. Alright, so the first clock cycle occurs and the first instruction is fetched. The second pulse occurs, add instruction is decoded and subtract instruction is fetched. Then the third pulse, add instruction is reading its operands, and third, at the same time, second instruction is decoded, right? Then the fourth pulse occurs, add instruction is being executed, there's a stall here, and then fifth clock pulse occurs, the add instruction is now writing its results. So during this entire clock cycle, this instruction, add instruction, is writing its results. So generally they would not have been available, the results would not have been available until clock pulse 6 began. But now what happens is, while it is writing the results, add instruction can also forward the operand to the subtract instruction, so that the subtract instruction can actually take R3 directly from the add instruction and start its own operation. So it doesn't have to wait like it had to in this case. So you see what happens here. Before writing completes, the add instruction can just forward the operand R3 to the subtract instruction so that subtract can also start its operation. Right now, subtract has read the operand which was given to it directly by add instruction, and then the 6th clock cycle, subtract is executed, and the 7th clock cycle, subtract has already completed writing its results. So this is what happens with operand forwarding. Without operand forwarding, you have to wait till the end of the first instruction, the complete end, before subtract instruction can get the necessary operand. But with operand forwarding, this instruction will simply forward its operand, the required operand, to the next instruction so that the next instruction can start its operation without having to wait. This is what operand forwarding is. Alright, the third kind of method that helps resolve data dependency conflicts is delayed load. Now, see, the responsibility for resolving conflicts in delayed load is given to the compiler, right? So it's the responsibility of the compiler itself. The compiler, it's the same compiler that translates high-level program into a machine language program. So while the compiler is translating your code into machine language program, it also takes care of data dependency conflicts. So it starts to keep track of all the instructions that will cause some kind of data dependency problem in the future. So during translation, it keeps an eye on that, right? So the compiler is designed to detect conflicts during translation, and then it reorders the instruction to delay the loading of conflicting data by inserting no operation instructions. See, you wrote a program and you don't know which instruction is going to cause data dependency conflict in the future. You just wrote a code and the compiler is now translating it, but the compiler knows which instruction could cause data dependency conflicts in the future. So while it translates your code, it also detects conflicts, and then during the translation process, it reorders the instruction. The same program will be executed, but in a slightly different manner. You'll get the result you intended, but it will be done in a slightly different manner just to accommodate for conflicting instructions. right? So it will make sure to reorder the instructions in a way that the instruction that would have caused some kind of conflict is now delayed so long that the conflict is now gone, right? So the conflict is what in this case? It's that the operand that is required is not yet available. So the instruction that would have required the operand is delayed, so that the instruction that was actually generating the operand gets enough time to finish writing that operand into memory. All right, so that is entirely the responsibility of the compiler in this case. All right, then let's move on to the next kind of hazard. So previously we discussed data dependency conflicts. Now let's move on to the third kind of hazard, branch dependency, also known as control hazard. Now from the name you can see it happens when there are instructions like branch or call or jump. Any instruction that drastically changes the value of the PC can cause a branch dependency or a control hazard. Now let's consider an example, right? So this is a hypothetical sequence of instructions. At 100th location we had instruction 1, and then 101, the 101st address we had instruction 2. This instruction happened to be a jump instruction. Then there was an instruction 3 at address 102, then we had several other instructions in between, and then at 250th location we had a BI1 instruction, right? Branch instruction. The expected output of this program, if you were executing this program, you can see that first you execute I1. So I1, I2, and since I2 is telling you to jump, you jump. So the expected output of this hypothetical sequence of instructions should have been I1, I2, BI1, right? So this is the expected output. Now let's see what happens in a cycle, pipeline. Right, so this is the pipeline. These are the instructions I1, I2, I3 and BI1, and at the first cycle I1 is fetched. At the second cycle I1 is decoded and I2 is fetched. The third cycle I1 is executed, I2 is decoded and I3 is fetched. Now let's see what happens. I2 is decoded. When you decode this instruction, you find out that this is a branch instruction, right? This is a branch instruction, but you know that only after you decode it, which happens here. But when this happens, the third instruction has already been fetched. So it has moved into the pipeline already, and you're only now finding out that it was a jump instruction. But it's too late because the next instruction line, whatever instruction it was, has been brought into the pipeline, and since it is brought into the pipeline, it will execute normally. See what happens in the fourth cycle. Instruction 1 is doing its memory operation, instruction 2 is being executed. Instruction 2, remember, it was supposed to be a jump instruction. So now instruction 2 is executed. Instruction 3 is being decoded now, but it should not have been instruction 3, it should have been BI1. So just because I3 was fetched in clock pulse 3, in clock pulse 4 it will start its decoding, then it will be executed, then it will undergo its memory operation. It will go on normally, and the output you get using the pipeline is this: I1, I2, I3 and then BI1. But this is what you wanted, right? So this is a conflict, this is a hazard that occurred just because of the jump instruction. So branch, jump and call instructions, it's very important to handle them properly, because once an instruction enters the pipeline, like I3 did, it will keep on going normally and will disrupt the entire expected chain of operations of your program. Alright, now there are several methods of handling these issues caused by branch, jump and call instructions. These are prefetch target instruction, branch target buffer, loop buffer, branch prediction and delayed branch. So we'll quickly take a look at each of them one by one. Let's first start with prefetch target instruction, and as you can guess from the name itself, prefetch target instruction. So what happens is, in this case, the target instruction is prefetched in addition to the instruction following the branch. That means if we take an example of this one, suppose this was a branch instruction. So I2 is fetched, then I3 is fetched, and BI1 is also fetched. That is what prefetch means, right? So you fetch the instruction which is the next instruction following the branch, plus you fetch the instruction that actually the branch instruction wants you to fetch. So you fetch both instruction, and then if the branch condition is successful, the pipeline will continue from the branch target instruction, and if the branch condition is unsuccessful, then since you have already fetched the next instruction, so the next instruction will be executed normally, right? So we fetch both instructions, the one following the branch and the actual target instruction. If the branch is successful, then the target is executed, otherwise the next instruction line is executed. All right. The second method of handling branch instructions is branch target buffers, BTBs. BTB is an associative memory, which I think you've already covered, or maybe it will come on later. So BTB is an associative memory. It is included in the fetch segment of the pipeline. So each entry of the BTB consists of the address of a previously executed branch instruction and the target instruction for that branch, for the previously executed branch. It also stores the next few instructions after the branch target instruction. Now, when the pipeline decodes a branch instruction, it searches the BTB also for the address of the instruction. If that address is found in the BTB, the instruction is directly fetched from this associative memory. If not, the pipeline shifts to a new instruction stream and then stores target instruction in the BTB. So if if you learned associative memories already, you know that they are very, very fast memories, and they are used when you need to access some resource repeatedly, right? So if you, whenever a branch instruction occurs, what happens is an entry is made in the BTB, right? And now if the new branch occurs, we see that whether the program has made a jump to that specific branch already, because that happens in programs, right? So more often than not, the same program makes a branch to the same subpart of the program. So if that happens, then this subcode can be executed repeatedly using the BTB. Otherwise, whatever the new instruction location is, that is fetched. Then there's a loop buffer. This is a variation of the BTB. It is a very small high-speed register file which is maintained by the instruction fetch segment of the pipeline. Now, when a program loop is detected, it is stored in the loop buffer in its entirety. The loop part of the program, the entirety of it, is stored in the loop buffer, including all the branches. The program loop can be executed directly. That means now, the next time that loop occurs, the next time, memory would not have to be accessed, and you can simply access that specific loop from the loop buffer. It's much faster, plus it makes your memory free to be used by other instructions. So since that specific instruction is not using the memory, some other instruction can use the memory. There will be no conflict, plus it will be faster because this is a very small, high-speed register file. All right. Then finally we have branch prediction, and you can guess from the name itself, it's about predicting branches. Now, a pipeline with branch prediction, it uses some kind of additional logic to guess the outcome of a conditional branch instruction before it is executed. All right. So before the execution of the branch instruction, additional logic is used to guess the outcome of this instruction. Then the pipeline begins prefetching the instruction from the predicted path, right? Prefetching you already know. So if the prediction is correct, you see that the branch has already been prefetched, so it will save time, right? There's no branch penalties. If the prediction is wrong, then no problem, then you can just go ahead with your the method of normal branch handling, right? Then there is delayed branch. Now, delayed branch is a procedure most commonly employed in RISC processors, so reduced instruction set computers. What happens is compiler detects the branch instructions and it rearranges the code sequence by inserting useful instructions that keep the pipeline operating without interruptions. So the compiler will detect the instructions and based on the presence of any conflicts, it will rearrange the code like it did in case of data dependency conflicts. It rearranges the codes by inserting some other instructions between the branch so that the pipeline can keep operating without any kind of interruptions. Let's try and solve a problem now to see how well we understand these concepts. Consider a pipelined processor with 4 stages: instruction fetch, instruction decode and operand fetch, execute and write back. The IF, ID and WB stages take 1 clock cycle each to complete the operation. The number of clock cycles for the EX stage depends on the instruction. Now, in case of add and subtract instruction, EX takes 1 clock cycle, but in case of multiplication instruction, EX takes 3 clock cycles. Operand forwarding is used in the pipeline. What is the number of clock cycles taken to complete the following sequence of instructions? So these are the 3 instructions that we are supposed to perform using a pipeline. The number of stages are given. We have 4. Number of clock cycles for each of these stages is also given. We have to calculate the number of clock cycles required. Now see, we have already done these kinds of questions in the previous videos where clock cycles were to be counted, and as you might remember, we used a phase time diagram. So this is the kind of table we are going to draw. These are the stages of the pipeline given in the question itself, and here we are going to count the number of clock cycles it requires. Alright, so let's see how we are going to execute these instructions. Now, when the first clock pulse occurs, the first instruction is fetched. Alright, I1, which is the add instruction, is fetched. Then the second clock pulse occurs. The first instruction moves on to the next segment of the pipeline, which is instruction decode and operand fetch. The second instruction is then fetched. That's how pipelines work, right? When the third clock pulse occurs, the first instruction moves on to the next segment of the pipeline, which is execution. Instruction 2 also moves on to the next phase, which is from instruction fetch to instruction decode. And since instruction fetch segment is now empty, it will take in the next instruction, which is I3. Now, you might have noticed something interesting at this point. Take a look at instructions 1 and 2. Instruction 1 says that R0 and R1 should be added, the result should be put in R2. Then instruction 2 uses that R2, multiplies it with the content of another register R3 and moves the results into R4. So this is, say, the same register. So the source operand for multiply instruction, that is instruction 2, is the same as the destination operand for the first instruction. And here what's happening is, while instruction 1 is being executed in clock cycle 3, while instruction 1 is being executed, instruction 2 has moved to the phase where instruction decoding and operand fetching is done, right? Instruction decoding and operand fetching. Operand fetching means R3 and R2. These are the operands for I2. But see, the add instruction is still being executed, which means this operand is not yet available. But I2 is fetching it. How is that possible during the same clock cycle? This is possible because of operand forwarding, sorry. This is because of operand forwarding. You see, we discussed operand forwarding before. So without operand forwarding, there are stalls in the pipeline. So until I1 finishes its execution, I2 will not be able to move on to the next phase. It will have to wait. But because of operand fetching, we can see that during the same clock pulse, while I1 is being executed, while addition is being done, this instruction has moved to its decode and operand fetching phase, and that is just because of operand forwarding. Right? So this is the use of operand forwarding here, and this is important because if we hadn't used operand forwarding, then this wouldn't have happened, which means there would have been a stall, and then the number of clock cycles would have changed, the final count would have changed. So it's very important to keep under consideration. If it's given in the question that operand forwarding is used, the clock cycle count will change accordingly. All right. Okay, let's move on to the next clock pulse now. What's happening in the next clock pulse? I1, again, it's moving into the next phase. I2 is also moving into the next phase. I3 is also moving into the next phase. Another interesting thing now what's happening. See, look at instructions 2 and 3. Look at instructions 2 and 3. 2 is writing some result in R4, and that result is used by instruction 3. Again, this would not have been possible if operand forwarding had not been used. The only reason I2 and I3 are being able to be in the same pipeline, in the same clock pulse, is just because of operand forwarding. Otherwise, I3 would have to wait. Right? So this is all because of operand forwarding. So this is how your operand forwarding affects your phase time diagrams. Very important to understand. Keep it in mind at all costs. Whenever there are shared resources in your given sequence of instructions, you have to keep under consideration how that would affect the overall cycle count for those instructions. All right, so in next clock pulse 5, you see instruction 2 still executed, and in 6 also instruction 2 is being executed. Now why have we done this? Why have we taken 3 clock cycles to perform execution of instruction 2? It's given in the question. See, it was written in the question that the execute stage depends on the instruction being executed. For add and subtract instructions, EX stage requires 1 clock cycle. So EX required 1 clock cycle for addition. It will require 1 clock cycle for subtraction when the turn for subtraction comes. But right now we are talking about multiplication, and multiplication requires 3 clock cycles for the EX stage. So in clock cycle 4 and in 5 and in 6, I2 is still in its execution state. And then clock cycle 7 occurs. And then I2 moves on to the next phase, right? And then only I3 can actually start its execution. So it has to wait for this, and then it will start. And it will also take 1 clock cycle, because again this was given in the question. Both add and subtract require 1 clock cycle for EX. It's only multiplication that requires 3, so we have to compensate for that, right? And then finally in the 8th clock cycle, I3 is writing its results. All the other instructions have completed their execution. So how many clock cycles did we require to execute these instructions with operand forwarding? It's 8. Alright, so it's very important, these kinds of questions, to keep in mind what the sequence of instruction is, whether or not there is some kind of dependency, and whether operand forwarding is used to handle that dependency or not. Because if operand forwarding is not used, then you have to introduce stalls, and then your cycle count will increase. Alright, so that's it for this video. Just a quick recap. In this video we talked about pipeline hazards. We discussed 3 main kinds of hazards and the methods of their resolution, and then we handled a sample problem.